The James Webb Telescope, a marvel of space science, stands out as the world's leading observatory. Its mission is to delve into the mysteries of both our solar system and distant worlds orbiting stars, and to explore the complex structures of our universe and our role within it. Tasked with uncovering the deepest secrets of our solar system and the distant galaxies beyond, it continues to challenge and redefine our perception of the universe and our place in it. Recently, scientists turned its powerful gaze towards a star system located about 120 light-years from Earth. What they discovered caused waves of excitement and intrigue in the scientific community. The telescope has found compelling evidence of carbon-based molecules in the atmosphere of a distant exoplanet, strongly suggesting it could be an ocean world. This extraordinary discovery deepens the mystery surrounding potentially habitable planets beyond our solar system. The exoplanet in question is K2-Cis 18b, a celestial body that has intrigued astronomers for years. Now, with this new discovery, interest in the planet has only increased, as it offers the tantalizing possibility that conditions could support life. K2-Cis 18b orbits a cool red dwarf star known as K2-C 18 in the constellation Leo. Its location within its star's habitable zone, the region where conditions may allow liquid water to exist, heightens the interest in the planet. This super-Earth is about 8.6 times heavier than our own planet, occupying a unique category of exoplanets that lie between the size of Earth and Neptune. What makes K2-Cis 18b particularly intriguing is the composition of its atmosphere. Using its unrivaled infrared sensitivity, the James Webb Space Telescope has detected the presence of carbon compounds, specifically methane and carbon dioxide, in the atmospheric envelope of the exoplanet. This points to the possibility of a hydrogen-rich atmosphere covering a planet covered in oceans, a configuration that could support life, or at least the type of chemistry associated with it. The discovery builds on earlier data from NASA's Hubble Space Telescope, which provided the first glimpse into K2-Cis 18b's atmosphere and opened the door to deeper analysis. However, while Hubble laid the groundwork, it was Webb's advanced spectrographic capabilities that provided the most detailed data on the atmosphere of a habitable zone exoplanet to date. One of the most intriguing aspects of the new discoveries is the potential presence of dimethyl sulfide DMS, a molecule that on Earth is produced primarily by marine organisms, particularly phytoplankton. While evidence for DMS in the atmosphere of K2-Cis 18b remains preliminary and unconfirmed, the very idea that a biosignature gas could be detected from such an incredible distance has excited researchers from multiple disciplines. If confirmed, this would be an unprecedented step forward in our search for extraterrestrial life. However, scientists are understandably cautious. The planet's structure, likely with a mantle of high-pressure ice similar to Neptune, covered by a thin hydrogen-rich atmosphere, could still be inhospitable despite the potential presence of oceans. These extreme conditions could make any liquid water inaccessible or uninhabitable for life as we know it. The technological triumph of detecting such complex atmospheric signatures remains undeniable. The method used is based on a phenomenon known as a planetary transit, where a planet passes in front of its host star, from our perspective causing a small drop in observed brightness. During these transits, some of the starlight passes through the exoplanet's atmosphere before reaching us. This starlight carries valuable information about the composition of the atmosphere, since different molecules absorb specific wavelengths of light. UEBA's instruments can capture and analyze these subtle changes with amazing accuracy, offering information that was previously impossible to obtain. Future observations using UEBA's mid-infrared spectrograph are expected to further improve our understanding of the atmosphere and climate of K2-Cis 18b, possibly confirming the presence of molecules such as sulfate. The ultimate goal of these ongoing studies is nothing short of revolutionary. They aim to determine whether habitable exoplanets exist and, if so, whether they show signs of life. But the telescope's discoveries are not limited to nearby exoplanets. In another groundbreaking observation, astronomers using UEB have detected complex organic molecules, particularly aromatic hydrocarbons, in a distant galaxy that formed when the universe was only about 10% of its current age. These molecules, which on Earth are associated with oil, coal deposits, and pollutants such as smoke, were previously thought to be too complex to exist so early in the history of the universe. Their discovery fundamentally challenges prevailing cosmological models, suggesting that organic chemical complexity arose much earlier than we once thought. The molecules discovered are not simple compounds like water or carbon dioxide, but instead are large molecular structures made up of tens or even hundreds of atoms. These are some of the most complex organic molecules ever observed in space, and their presence in such a young galaxy raises profound questions about the ability of the early universe to support the building blocks of life. The light carrying the signature of these molecules began its journey less than 1.5 billion years after the Big Bang, the IR instant in cosmic terms, given that the age of the universe is estimated about 13.8 billion years. That astronomers can now study this ancient light in such detail is a testament to UEBA's extraordinary sensitivity and technological sophistication. Previous attempts to detect organic molecules in ancient galaxies could only establish their general presence. But the UEBA telescope allows scientists to pinpoint where these molecules are located in their galactic environment. One particularly puzzling discovery is the uneven distribution of these molecules in the galaxy known as SPTZIG 4418 DEF. The irregularity adds another layer of complexity, hinting at processes we don't yet fully understand. Even more astonishingly, this early galaxy appears to be as massive as our Milky Way, and already contains stars that have produced as much carbon and oxygen as those in our galaxy today, despite being only a tenth of its age. Such discoveries suggest that galaxy formation and chemical evolution may have occurred much faster in the early universe than previously thought. Taken together, the discoveries of carbon-based molecules on K2-Cis 18b and complex hydrocarbons in the primordial galaxy offer a dual perspective on the potential origin of life. One is based on the search for habitable planets in our cosmic environment. Another looks deep into the past to understand how the basic ingredients for life emerged in the early universe. These breakthroughs not only expand our knowledge, but also raise new questions about how common life-bearing worlds might be, and how quickly the universe became chemically enriched. The James Webb Space Telescope has revolutionized the way we explore space. With every observation it sends back to Earth, it challenges scientists to re-examine long-held assumptions and consider the possibility that life, at least its ingredients, may be far more common than previously thought. The ability to detect subtle molecular signals from planets tens or hundreds of light years away, and from galaxies that existed nearly 13 billion years ago, reflects an extraordinary leap in our technological capabilities. These achievements are more than just academic achievements. They represent humanity's quest to understand the cosmos at its most fundamental levels. The discovery of carbon compounds in the atmosphere of K2-Cis 18b may not prove the existence of life, but it does bring us closer to answering that age-old question: are we alone? Meanwhile, the discovery of complex organic molecules in one of the earliest galaxies adds a new dimension to our understanding of cosmic history, suggesting that the chemistry of life was already in place when the universe was still in its infancy. As astronomers prepare for deeper exploration and await further data from UEBA's mid-infrared instruments, anticipation is growing. In the coming years, the telescope may reveal even more amazing secrets that will continue to redefine not only our knowledge of the universe, but our understanding of the potential for life throughout the cosmos. With each new milestone, the James Webb Space Telescope confirms its role as a cornerstone of space science, pushing the boundaries of what we know and what we dare to imagine. It links the distant past with the distant future, linking the chemical complexity of the early universe with the atmospheric mysteries of worlds not yet visible. In this way, it openly invites us to continue to explore, question, and dream. When we look at the sky with our eyes, we do not see just stars and planets. We see the possibilities of new discoveries, the potential for life beyond our world, and the mysteries that await us in the cosmos. The James Webb Space Telescope is our tool to explore these possibilities, to uncover the secrets of the universe, and to answer the questions that have puzzled us since the dawn of humanity. It is more than just a telescope. It is a testament to human curiosity, a symbol of our unending quest to understand the cosmos, and a beacon of hope for the future of space exploration.